Lions Rock Productions.
This is Jay Moore.
This is Greg Cruz.
This is Bryce Vine.
This is Dexter from The Offspring.
This is Nathan
This
East.
is Sebastian Younger.
This is Daryl
This is Stuart Copeland.
This is Mick Gillette.
This is Andy Summit.
This is Dr. Bob Greenberg.
This is Gabby Reese.
This is Rob Bell.
Hey, this is John Leon Guerrero.
Hey, and this is Pete A. Turner.
I'm Dr. Andrew Friedman. I'm a research scientist at UC San Diego at the Center for Astrophysics and Space Sciences. With our team, we recently completed a crazy experiment, which we call the Cosmic Bell Test, which is testing something fundamental about quantum mechanics, our fundamental theory of nature at the smallest scales, and I'll talk about today on the Break It Down Show.
And now, the Break It Down Show with John Leon Guerrero and Pete A. Turner.
Yes, we are here at UCSD in your office. Thank you for hosting us. And I'm sitting next to my co-host, a lifelong friend, someone that I care dearly about, who's been in the background, but now officially on the show is David O. West, also a UCSD grad.
Yes, thanks for the invitation to come here. And after getting this microphone on my head appropriately, I think I'm able to perform as you expect. So thanks for the invitation.
We'll see about that. Anyhow, yeah, this is interesting, and really, it's fun to push myself outside of the norms. Of course, you're a mutual friend with Brian Keating, Dr. Brian Keating, who's actually going to be tomorrow's guest and on a follow-up episode talking about the Nobel Prize and the challenges therein. But let's get on to your stuff. You cover a lot of ground. You also we talked to another cosmologist, a theoretic guy in Dr. Stephon Alexander. So it's interesting to have the two of you guys kind of come on and kind of compare and contrast what you do, because you're working on the same big problems, but the problems and the questions are so huge, you don't have to be anywhere adjacent to each other and still be talking in the same field. Tell us, so that us dumb folks can understand, tell us what you do.
Yeah, so I'd say the big picture is that I'm a cosmologist. And cosmology is the study of the entire history of the universe, all the way from the Big Bang 13.8 billion years ago till today. And so we're talking about the structure of the universe on the largest of scales. We're talking about the evolution of the universe on billions of year time scales. And, we're interested in how everything started and how everything evolved. So we get till today when we have planets and stars and people, and we're interested in the biggest questions of all in terms of, life in the universe. How likely is it, that we came into existence? We're interested in the origin of the universe. We're also interested in the far future of the universe. In billions or trillions of years, what's going to happen if we extrapolate our best physical theories? So cosmology is the field that it really started in the 1930s, when Edwin Hubble and others were able to help us understand that our own galaxy, the Milky Way galaxy, which has about 400 billion stars, is not the only galaxy. That there are many other galaxies. We now know of 100 billion other galaxies in the part of the universe that we can see, and these galaxies are all moving away from each other. So that's what we mean by the universe is expanding. And we also think that the expansion of the universe, it was always expanding, but in the first few billion years of the universe, it was slowing down. But now it's speeding up. And so cosmologists are interested in this question of the history of the expansion of the universe, and then this new phenomenon, what we call cosmic acceleration. And so my PhD thesis was using exploding stars as a way of mapping the history of the expansion of the universe. And so that's kind of where I got my start, in observational astronomy with robotic infrared telescopes and optical telescopes measuring exploding stars, which, if you measure the light of an exploding star in another galaxy, if it's many millions or billions of light years away, you're not seeing it as it is now, but as it was when the light left long ago. So every one of those observations tells you sort of a snapshot in the history of the expansion of the universe, and you can make a movie of the expansion history. So that's where my background is coming from. But in cosmology, we're interested in not only the biggest things, we're interested in the smallest scales as well. And so we sort of had two big theories of nature. Einstein's theory of general relativity, which describes gravity on the largest of scales. That's what we used to describe the expansion of the universe. And then we have quantum mechanics, on the other hand, which is our best theory of the subatomic world. And there are lots of questions where these two theories intersect, but there are areas where they disagree very strongly. So we think that neither of them is the final theory of the universe. People are searching for a so-called theory of quantum gravity that would unify the two together. There's so many different rabbit holes you can go down in cosmology and in astrophysics and in studying fundamental physics. So I would say that the biggest thing that defines the kind of research I'm interested in is using cosmology, using the largest scale of things in the world to learn new things about the fundamental nature of physics, about quantum theory, about general relativity, about what's causing the universe to expand and accelerate. We can talk more about quantum mechanics, but there's so many mysteries in quantum mechanics. There's so many weird phenomena.
Well, let me ask you this then. So we've got the quantum mechanics thing, and there are so many questions that we have answered. How long? Give us a sense for how long does it take to? I know there's like iterative change all the time. You know, someone's paper adds a piece to the puzzle, and so all of a sudden someone finds a piece that's way off the map, and you're like, oh, that's the big leap. In the next 20 years, we'll be filling that part in. Is it 20 years? I mean, you're a relatively young guy. Kip Thorne is a relatively old guy. You guys work in the same kind of field, but again, not in the same vein. Is it a 40-year proposition to try to get to some of the answers, or to accumulate the pieces that get to the story that you're trying to tell?
Yeah, so for some perspective, so quantum mechanics as a theory has been around for about a century. You're asking a very good question, but a very hard one to answer, which is, how long till the next major breakthrough?
Yeah.
The national governments and funding agencies would love to know the answer to this question, but the truth is nobody knows. But in terms of how long would it take to solve the major outstanding issues that I was bringing up, I would guess many decades.
Right.
With quantum mechanics in particular, it's the best tested theory humanity has ever constructed. So when you look at some of the predictions of quantum mechanics and quantum field theory, which is a more advanced version of it that incorporates Einstein's theory of special relativity, there's some predictions that are unbelievably precise, where you can know the property of some subatomic phenomenon, to 15 decimal places. And
yeah.
You do the experiment and the prediction is spot on. And that quantum mechanics, by some people's estimation, it's enabled so many technologies that are just part of our daily lives now that I've heard estimates that 30 to 40% of the GDP of the world is enabled by technology that requires quantum mechanics to understand and build. So we're talking about lasers, computer display screens, your smartphone, satellite communications, computer circuits, anything that involves understanding and manipulating phenomenon at the molecular and atomic level. It often involves understanding quantum mechanics. So we know how to use it to build things, but it's a very weird theory in many ways compared to the kinds of physics that we would call classical physics. This is like billiard balls smacking into each other, or
right.
Things rolling down inclined planes. The physics of Isaac Newton that many of us learned in high school. The biggest difference is that classical physics is what we call a deterministic theory. If you know the initial conditions of the system, we can use the equations of the theory to predict the future outcomes. The more precisely you know the initial conditions, the better your future predictions will be, and the farther out in time you'll be able to predict. In quantum mechanics does not tell you. Let's say you have an electron, a charged particle that many electrons orbit around nuclei and create atoms. Quantum mechanics can't tell you, in 5 seconds the electron is going to be over there. It can only tell you the probability that it'll be within some region. And so you have immediately something that's very, very different. And so something that's kind of embarrassing to many of us in the community is that although we can use quantum mechanics to build amazing technologies, there is literally no consensus amongst experts on what the theory means and what it's telling us about reality, what it's telling us about the world. I'm particularly interested in that, and the thing that I found very fun about working on this particular cosmic bell experiment is that there's a way of using cosmology as a whole, the large scale stuff in the universe, to test something interesting about quantum mechanics. And many people in the field kind of take this attitude of, well, the theory works, we can use it to build iPads, so why should we care what it means? It's the sort of shut up and calculate idea.
Yeah.
But many of us are also interested in this question of what does it all mean? And it may be that the world just is weird in the way that quantum mechanics describes. Maybe objects like electrons don't actually have a definite position until we measure it. Maybe they really live in this fuzzy cloud of probability that it could be there, it could be there. Maybe electrons are in multiple places at once, which is one of the standard ways of describing what the equations of the theory tell us.
Could be situational, momentary.
It could be. But we're accustomed to thinking of the world, when you look away from the moon, it's still there.
Mm-hmm.
So Einstein famously, was supposed to have said, to somebody who was advocating this other worldview of quantum mechanics where reality doesn't exist until a measurement is made, do you really believe that,
right,
the moon isn't there? And when you're not looking at it, and today we've moved further away from the idea of a human being having to observe a system in quantum mechanics in order for it to take on a definite state. Interactions with anything in the environment act like measurements that cause it to take on a definite state. But nobody knows how you go from this fuzzy cloud of probability to, when I make a measurement, it's actually there. Quantum mechanics doesn't describe that process. It's called the measurement problem, and it's the kind of thing that keeps philosophers up at night. It doesn't keep most people up at night.
Yeah.
I would say it doesn't keep me up at night either, but it keeps me awake during the day thinking about it.
So are you talking about things like spooky action at a distance?
So that's another phenomenon it's all part of this. So quantum entanglement itself is another weird feature of quantum mechanics, which Einstein himself called spooky action at a distance. The experiment that we did is fundamentally focused on testing something about this. So what is entanglement? So if you have a pair of particles in quantum mechanics, sometimes they can be two particles of light, two photons, or they could be an electron and a positron, which are charged particles. One of them is its antimatter partner. Let's stick with photons for the moment. So if you have a pair of entangled photons, and I send one off in one direction to one experimenter, which we often name Alice, and I send another one in the other direction to Bob, the second experimenter. If Alice measures something about her photon, she instantly knows something about a future measurement outcome on Bob's end. And the kind of thing you'd be measuring. So you guys have seen polarized sunglasses. So one property that photons have is polarization. So we think of the photons themselves as oscillating electric and magnetic fields. And the electric field, oscillates in a certain direction perpendicular to the motion of the photon, and that's the direction of polarization. So if I have polarized sunglasses, if you look at a monitor like this...
He's looking at a monitor right now.
I'm looking at a computer monitor, so some of that light is polarized, and if you guys can see, I'm rotating it in this direction, and it's blocking most of the light.
Right.
And then if I go back in this other direction, you get more and more light progressively, and then you get the most light over at this angle. When you have, individual photons one at a time, you can send them through devices that are very similar to this, that are very much like polarized sunglasses. They're oriented at some angle, and then you can ask the question, does it get blocked or does it go through? So if Alice makes a measurement like that, orients her detector in some angle, and it either goes through or it doesn't, essentially she's measuring the polarization of the photon.
So in simple terms, it's halted or it's deflected.
Well, it either goes through and then a detector like a CCD camera, like your digital camera on your phone, detects it, or it gets halted by getting absorbed inside the polarizing filter, like your sunglasses.
Gotcha.
So
is that why my glasses are so heavy?
It must be, yes.
Through photon absorption.
Yeah, totally. So many photons.
Yeah, it's definitely something to look into. But the weird thing about this is that, if you can talk about the photon's polarization being either horizontal or vertical.
Okay.
And so as soon as Alice measures horizontal, she instantly knows in a particular configuration that Bob's going to measure vertical, for example. And the thing that's weird about this is on Alice's side, it's totally random, 50-50, whether she's going to measure horizontal or vertical. But she instantly knows, no matter how far away Bob is, no matter how long ago the particles became entangled, what his future measurement outcome is going to be. And so it's kind of a mystery how the photons, how particles in entangled states maintain this coordination so far away from each other.
Right.
Now, early on in the 1960s and 70s, when people first started thinking about this, they were thinking, man, could you use this to send messages instantly really, really far away?
Sure.
That's a common trope in science fiction. Unfortunately, you can't, because you can't cheat relativity, Einstein's theory of that tells us that no information can go faster than light, precisely because the outcome is random on Alice's side. So she can't controllably influence what shows up on Bob's side. The best she can do is send a random string of ones and zeros, which would be a message that contained no information at all.
Right.
So, but even so, it's still weird how entanglement works.
And then when Ricky comes along and he's like, but you guys are talking in 2 dimensions, let's talk in 3 or multi-dimensions, polydimensional. Does that part of the entanglement as well is like we're sort of able to account for the vertical and horizontal, but now we've got to account for these other elements to time and a third or a fourth or a fifth or sixth dimension?
Well, if you talk about extra dimensions in space, you're talking about another direction that you could go that's perpendicular to the, up, down, left, right, side to side, that you would normally think of. And, physicists and mathematicians have long, played around with theories that have extra spatial dimensions. Usually people stick with one time dimension. People have sometimes messed around with more than one time dimension, but it's definitely possible. And many physical theories that are being played around with today do involve extra spatial dimensions. And one interesting way of thinking about entanglement is that perhaps there is a way that the particles are connected to each other through a direction which wouldn't manifest itself through the normal 3 dimensions of space. So in general relativity, Einstein's theory of gravity, there are solutions to the theory that involve things called wormholes.
Yeah.
So these are essentially shortcuts between 2 places in space and time. And there's some speculative research that people like Leonard Susskind at Stanford and Juan Montesana at Princeton are thinking about, that they're trying to ask this question of whether or not one could think of entangled particles themselves as being quantum-sized wormholes. And maybe that's why these effects persist, where you can have entanglement that the mystery is trying to explain, can you tell a story about how entanglement works? How is this coordination maintained between these things that are really, really far away? And so that's certainly one thing that people are thinking about.
So as you jumped into the experiment and talking about referencing Alice and Bob, I noticed that there's also the cosmic setting generators. Can you expand on that and sort of kind of put into context the greater picture of the experiment? And in these cosmic setting generators, what are they and what factors did you consider to choose them?
Sure. So ultimately, when we're making experimental choices in any experiment, whether it's an entanglement test or anything else, you have to decide how you're going to make those choices. People could make those choices, or you could have machines make the choices. Sometimes you'll have machines that have, what you'd think of as random number generators or pseudo-random number generators making the choices. It for various reasons, what we decided to do is it's a longer story for why anyone would do it this way. In our experiment, we're doing a standard entanglement test where you send entangled particles to distant detectors at Alice and Bob, and we're measuring the polarization of photons. And Alice and Bob each have 2 possible measurements they can make. Either have the sunglasses like this or move them like this. And then Bob has his pair of choices too. So we basically need a means to very rapidly choose in real time which measurements are going to be made on both sides. So we have millions of pairs of entangled photons per second that are being shot out of this entangled particle source that was built by our colleagues at the University of Vienna. And while the entangled particles are in flight, instead of letting something on Earth choose the measurement settings, we decided to point telescopes up at distant astronomical objects. We started in 2017 with a pilot test in the city of Vienna, where we pointed small telescopes, 8 and 10-inch telescopes, out of the windows of buildings and looked at stars in our own galaxy as sort of a proof of principle. And so the cosmic setting generator that we developed for that basically takes the color of the light. So, light has a certain wavelength, to our eyes that manifests itself as color. To our cosmic setting generator, we basically said, we're assuming that the color of the light was actually set long ago and far away when the light was emitted. And we basically say that if the light is a little bit, redder than some cutoff, we'll make that a 1 for our random number generator. And if it's a little bit bluer, it's a 0. And that corresponds to making a measurement with the polarizing sunglasses in the same position or switching it. It's done the same on both sides.
Mm-hmm.
And for various reasons, we have to do this really rapidly. So while the entangled particles are still in flight, there has to be a fresh random choice from astronomical light on both sides.
So there's no set trajectory on what you're looking at for the cosmic reference point.
Well, we do pick a particular... In our pilot test, we picked particular stars in our own galaxy, ones that were visible through these open windows at the right time, like in real time as we were doing the experiment. We recently did a larger cosmic bell test, sort of the full test, where we worked with the Roque de los Muchachos Observatory in the Canary Islands, and we were able to, very, very fortunately, be able to use very big telescopes with mirrors that were 3.6 meters and 4.2 meters. And with this, instead of just looking at stars in our own galaxy, where the light had been traveling for hundreds or thousands of years to us, we were able to look at distant galaxies, special galaxies called quasars, which are powered by supermassive black holes, which are eating gas and dust and heating up, and we could see them all the way across the universe. So we were able to look at those guys, and we were able to look at one that emitted its light 8 billion years ago and another that emitted its light 12 billion years ago. And so, but in both cases, the cosmic setting generator, we made some improvements, but it worked in the same way, where the color of the light, we're assuming it's set at the time of emission. The wavelength of the light actually does get stretched out by the expansion of the universe, but that doesn't affect our argument. The color that it would arrive to us today is set at the time of emission, and you can use that as a random number generator in real time. But in order to talk about why one would do it, we would have to go down the rabbit hole of something called Bell's theorem, and so Bell's theorem is a famous theoretical result in the 1960s by John Bell, a physicist who worked at the CERN particle accelerator, amongst other places. And he was interested in certain questions about, whether or not you could tell a story about what's going on at the subatomic level that would make sense in a way more so than the standard description of quantum mechanics. And so Einstein himself was very, very skeptical of quantum mechanics. He thought that quantum mechanics had to be incomplete. He thought that the idea of not being able to make definitive predictions about where particles were didn't make sense, so there must be something missing. And then he also thought that the idea of an object being in two places at once, what we call superposition, didn't make sense. And he wanted the world to have certain properties. So one of them is realism. The idea that the objective external world exists, and even at the subatomic level, things really have definite properties and positions and velocities and polarizations, even when you're not measuring them. So Einstein wanted that to be true. And he also was the architect of special relativity, which is a theory which basically says that you can't send information faster than light. So if you have two distant systems, nothing you do to one system can instantaneously affect something far away. It's got to have time for some signal to propagate between the two. So Einstein wanted a worldview to be, in his terms, local, so that things can interact when they touch each other, when they're right up next to each other in space. A worldview that involved something that's non-local would involve spooky action at a distance.
Right.
where even if you can't use this to send information faster than light, there's still some weird thing going on. So when he thought about entanglement, he and his colleagues Podolsky and Rosen wrote a famous paper in 1935, where the so-called EPR paper for their initials, where they talked about entanglement, why they thought that it implied that quantum mechanics as a theory couldn't be complete. For many years, people thought about this and thought it was just sort of a philosophical problem, that it couldn't have any practical consequences whatsoever. But what John Bell did is he formalized Einstein's ideas about what he wanted the world to be like in a more mathematical way. And what he did is he actually showed that if you make certain assumptions about the world that are very much like Einstein wanted, that you could design an experiment, an entanglement test, where you do something similar to what we described, that would actually give different predictions if quantum mechanics was true versus this other worldview, the so-called local realism worldview that Einstein wanted. And so, so
it's like an if-then test kind of thing?
The thing is that you can ask this question of, if you do an entanglement test, you can look at Alice's measurements and Bob's measurements, and then you can see how often they line up. You can do this hundreds of times, thousands, millions of times, and you look at the correlation between the measurements that they make. Essentially what Bell showed, you can cast this as a game where, let's say that you're the particles themselves, and you're trying to win the game by having the measurements agree as much as possible, for example. What strategy can you come up with in advance in order to make that happen? And if you use the assumptions that Bell made, you can only win the game 75% of the time. But if you look at quantum mechanics, and then you ask, for a quantum mechanically maximally entangled pair of particles, how often could they win the game? They could actually win it 85% of the time. So that's a 10% difference. It might not seem like much, but it seems like there's no way of explaining what the hell's going on if the worldview is more like what Einstein wanted and that what John Bell was trying to formalize. So John Bell basically said there's an upper limit to how often the measurements could line up.
This episode of the Break It Down Show is brought to you by Lions Rock Productions.
That's us.
We publish, evaluate, and develop podcasts just like this one, consult others to build their own, and create associated content and content marketing strategies.
So if you're launching or expanding your social media presence, your business or your personal brand, or if you just want to take your media presence to the next level,
reach out to us on Twitter
at Pete A. Turner
or at JohnLG69
at the Break It Down Show.
There's 1,000 ways to get a hold of us.
Now enjoy the show.
There's an upper limit to how often the measurements could line up if the worldview was a simple worldview that made sense to Einstein. But then when we do the experiments, we see that you get more correlation than that, which is consistent with quantum mechanics. It doesn't tell you that quantum mechanics is right, but what it tells you is that at least one of the assumptions that Bell made about the world is wrong. So there's a third assumption that I should talk about more, which is sort of the main thing that motivated our experiment. So Bell also assumed, Einstein implicitly assumed this, but Bell assumed that, when you're making your measurements, when you're choosing, where your sunglasses are in the polarization entanglement experiment, that these are so-called free choices. What does it mean for it to be a free choice? In this context, it means that there's nothing in the universe that's missing from quantum mechanics that could influence those choices and then also influence the outcomes of the measurements. So it turns out that this is a really strong assumption because we all, if you think about any choice that you made, are you willing to say that it wasn't influenced by anything in the past?
Yeah, right.
We all live and evolve in this same universe, and so things in our past that have been able to causally influence us, we have so many things in our past that influence all of our choices, and that's just on the human side. But if you think about any kind of mechanical system, that's true too. There's lots of stuff in its past that could influence it. So the conclusion from doing these experiments and seeing that the measurement outcomes line up more, that the upper limit from Bell's inequality in technical terms is violated, it tells you that at least one of the assumptions about the world that Einstein and Bell wanted has to be wrong. So either realism is false, so objects do not have definitive properties and positions before you look at them, so the world is sort of fuzzy in that way, or the world is non-local, so that it really is possible for spooky action at a distance to do things without technically violating relativity, but it's still weird. Or the third, way out is if your choices in an experiment aren't as free as you thought. For a long time, many people thought that this would mean that you have no choice whatsoever. But recent theoretical work that colleagues of mine have done and that I've worked on has shown that you can still salvage the worldview of Einstein and Bell. You can keep locality, you can keep realism, so the external world exists and relativity is true, by giving up a little bit of freedom of choice. So the analogy I would make is that, let's say you go to a restaurant and, it's a Mexican restaurant and you're like, okay, I'd like there's 10 things on the menu and you think, okay, well, I'll have the chicken burrito. And then they tell you, actually, we're out of chicken. And so you realize that you thought you had 10 options, but now you only really have 5 options.
Yeah.
So the degrees of freedom you could choose from are limited in a way that you didn't know. You still have...
is the Al Pastor good?
Yeah, that's true.
Because if it is, I'm pretty happy. All right,
I think you'd be okay with that.
Let me ask you a question, because you just said a lot of things, and it's incredible to know that there's someone thinking about these problems and trying to figure out if Einstein was right or wrong. And the things that I've learned about the world just from doing things is that there are details inside the details that house details that you can only get into if you truly become an expert in that area. Like I can go out into a conflict zone and I can start to see reality that you couldn't see because you don't have that triple detailed eye. So one of the things that I have to do is come up with analogies like you just talked about all the time. You must constantly be looking for ways to describe things in ways that make sense to a big dummy like me, where I'm like, is it like pigeons all in the city? And you're like, no, dummy. But this is what I really want to know. Where do your analogies come in? Is it when you take a nap? Is it in the shower? Is it when you're running? Where do your best analogies, where are they born?
I think that... You're absolutely right. When you're trying to translate scientific, philosophical, mathematical concepts, to somebody without that background, it's really like trying to translate between foreign languages.
Yeah.
And as far as where the best analogies come from, sometimes it's from reading books where other people have already thought of something that really works. But I think in my case, it comes mostly from just talking to random people about this, especially people who don't have that background. And then just trying things out and seeing if it works, and that sometimes there are limits to how far an analogy can go without actually diving into the mathematics.
Right.
A surprising amount can be described in plain English words. I certainly know that just because I've said something out loud doesn't mean it's been understood.
For sure.
This is stuff that's tricky, where experts disagree on this. So that for somebody not trained in this, you guys are not dummies if any of this stuff seems far out.
I have to say that in my pre-research of us getting to learn a little bit about where you're coming from and what you're doing, my background being mechanical engineering as my core, I appreciate what you're doing and what the community you're part of is doing in exploring and helping educate others on this topic. And if there's a way to simplify this, I believe it for me is a good thing, and it's a positive thing for school age kids all the way to the 100-plussers. People should be thinking about this, and it seems in some way, shape, or form everyone is. So I just want to say I appreciate what you're doing and how you're applying it, as well as the humility of which you're approaching all of this, because it's really nice to hear that the old school thinking is that a person with a PhD sits around, in the evening and starts arguing theory with a bunch of old crusties, and it's not the type of person you are by any means. And so I think you're sort of, in my opinion, leading the next generation of open-minded thinkers, and maybe even creating a revival of looking beyond just the immediate, electronics in our face, and taking a moment to stare out into space and really contemplate what's happening in the universe.
Yeah, thank you. I'm glad to hear that that's your reaction to things. I think that humility is incredibly important. I'm glad you mentioned that in science, because science is the most humbling thing I think any human can do. Because I think if we're all honest, we're all ignorant of most things. The amount of stuff that there is to know is just so unbelievably vast. Like the ship sailed a long time ago where like an educated person could know all that's known.
Yeah.
I mean, that ship sailed like, I don't know, the 15th century or something.
Right.
So the more that I learn, the more that I realize how little that I know. And, you know, the unknown unknowns to most people, many of them are known unknowns to me because I've looked down the rabbit hole. But I do think that, you know, if people have basic curiosity about all this stuff, especially kids, you know, from a young age, and I wish as a society that we encourage that more. I think everybody has the capability of thinking about all these things at a level that's right for them. And I wish that more people had that opportunity. So many people struggle with, you know, making ends meet on a day-to-day basis. I would never like tell somebody that, you know, why aren't you like thinking about philosophical questions all the time? I mean, if somebody's working, you know, 5 jobs just to try to feed their kids, if somebody lives in a war zone, if somebody, you know, lives in an oppressive culture, you know, where they aren't given the freedom to think about things, then, you know, I consider them to be, you know, in a very unfortunate situation. I wish more people had the time and the luxury. So I consider myself incredibly lucky to be able to, you know, to think about these things. And I really, I think that humanity would be better off if people were freer to be able to explore all these kinds of things, you know, to the best of their ability.
As you do explore, then people in the building are all exploring, and then the other campuses, Stanford, MIT, all these places where all this exploration is going, we're creating the raw materials that will be put into our hands in forms of electronics, and quantum computing is a thing. And the pace is one of my shows. It's called Popping the Bubble. Everybody should listen to it because it's really super good. But one of these innovation guys is talking about the speed of innovation exceeding the speed of automation, and as long as that happens, we'll be all right. And the thought is we'll have more time to have some of these kind of conversations because a lot of the, I'll just say, the mundane things that we're doing today will be handled. And there's so many things like that. Like when I get gas, I don't have to take cash into a person who takes a physical machine, and that's all those mundane things are already gone from our lives. So there'll be more of those things. And I would imagine in your world, the ability to rely on a computer to give you a true answer, you would have to do less of the heavy lifting yourself and maybe compress a lifetime's worth of research and knowledge into a smaller time frame where you're able to juggle several lifetimes because the computer is creating models, that kind of thing. So maybe there will be more time to do that, and we'll never run out of things to try to figure out. But when you do look at what we are able to do now, and we kind of look forward at a percentage of, let's say 0.5% a year of improvement, you know, we're going to learn a lot more about all of these things. What kind of future do you see as we do these tests and we learn more about Bell and the distinction between the Einsteinian world and the Bell's world and the other worlds that are going to clearly come out of all this experimentation and thought?
Yeah, and if I could kind of
do it,
paraphrase on that question, I'm curious, where do you see technology applied in this experiment and beyond, where it's really setting the cornerstone or a foundation of or building upon what's already been done? But where do you see our future going with the application?
Yeah. So there's a lot to unpack. Those are great questions. So
good job.
I haven't yet talked at all about the technological applications of quantum mechanics and entanglement. I'm personally most interested in the philosophical questions in terms of what does it mean about the nature of reality. One of the reasons why you can get funded to work on this, amongst other things, is that there are huge, potentially world-changing applications to quantum technologies.
Let's be honest, because people can monetize on it.
Well, yes, yeah, absolutely. There's no doubt about that. So, quantum computing is one huge application. So, quantum computing fundamentally relies on entanglement, and there are many different things that quantum computers could potentially do. They could simulate quantum systems that are extremely difficult to simulate with classical computers. That's going to potentially have major implications for designing atomic and molecular technologies, designing drugs, where we understand how everything interacts with it would be really hard to write down and solve equations in the standard way of doing things. But a quantum computer might be able to simulate, a new drug molecule, for example, and we'll actually know how it works. We might be able to learn how proteins fold, and we might be able to build a new tiny miniaturized technology that we've simulated on a quantum computer. But the killer app that many people have talked about since the early 90s is that, today, encryption is a big deal. So all of the online bank transactions that we send over the internet are encrypted, and that, many different types of communications are encrypted. And so basically, encryption is designed to try to make your message secure so that a third party can't hack into it and eavesdrop and learn your message. So the current encryption technologies essentially all boil down to forcing a would-be adversary to solve a really hard math problem. It's the kind of math problem that's so hard that if you tried to solve it on your laptop, it would take longer than the age of the universe. So,
right.
There's some interesting...
7. Done. Sorry. Go ahead.
Yeah, so there's some so a good example is the problem of factoring. So if I take two numbers and I multiply them together, that's pretty easy on a computer to do, even with really big numbers. And if I take two prime numbers that are only divisible by themselves in 1, and I multiply them together and I get another bigger large number, it's easy to do it in one direction. So you got this huge number. Let's say you got a 200-digit number. But if I then give you that 200-digit number and I say, tell me what the unique prime factors are, that's a really hard problem.
Yeah.
The larger the number gets, you could design a number so large that, it would take, the world's computational resources, trillions of years to solve. But in 1994, a mathematician, Peter Shor, came up with an algorithm on a quantum computer that could potentially solve this factoring problem very rapidly.
Huh.
And no one has yet built a quantum computer that can do that. It's a really hard engineering problem to isolate the various components of the quantum system from the environment. So entanglement is relevant in many ways because you want different parts of the quantum system to be entangled with each other. But if I make a measurement on, let's say a pair of photons that are entangled with each other, then my photon becomes entangled with the measuring apparatus. And so interaction is one way of creating entanglement. I mean, and fundamentally entanglement means that the systems cannot be described as independent of each other anymore.
Right.
They're bound.
Inextricably bound together. The entanglement very, very rapidly, by interacting with things in the larger environment, dilutes and spreads out. If you have two things that are maximally entangled with each other, they can't be entangled with anything else. So if any of those things interact with something else, then the entanglement starts getting diluted. So for a quantum computer, you want to isolate things from the environment, do the quantum computations, and then only make the measurement at the very end when you're going to get the answer out. And that turns out to be a really hard engineering problem. The number of qubits, so a qubit is an analog of a classical bit that can be 1 or 0. A qubit can be some fraction of 1 and some fraction of 0 at the same time. And you can do these weird computations, like solving the factoring problem, fundamentally because of that property. You may need a quantum computer that has hundreds of qubits or thousands of qubits before you can efficiently solve the factoring problem, like in a matter of minutes, for example. But every 3-letter agency in the world, every national government, every big corporation is really interested in this, and there's a lot of new investment in research and development. Google, IBM, there's a Canadian company called D-Wave. There's a million quantum startups that are trying to build quantum computers, and breaking all of the world's current encryption codes by solving things like the factoring problem very rapidly is a killer app of quantum computing.
Yeah.
But entanglement itself can also be used to replace all the current encryption schemes that exist with a new type of encryption, quantum encryption, that in principle could be perfectly secure. So, if Alice and Bob are trying to exchange messages, and Eve, a third-party eavesdropper, is trying to, intercept their communications, with these new protocols, what would happen is that you could still do a denial of service attack where you could disrupt the communications, but that there's no way that Eve could intercept the message without, let's say, Alice knowing that the message was being messed with, and Eve would destroy the message in the process of doing that, so that the security of the message would still be maintained in these systems. But the question of whether or not quantum computers will work as advertised and whether or not quantum encryption will actually be as secure as advertised actually hinges upon these philosophical questions that we were talking about. So,
right. And things like we're going to invent web TV, and it's nothing like what we thought it was going to be, but we do have something else. And maybe quantum computers become a completely different thing. And I was going to ask, so if we're talking about encryption and we're trying to separate entanglements, is there something? I don't know, let's say Seymour is trying to see more of the quantum zone, and he's trying to encrypt by doing quantum bonding and grabbing different things and then stacking and layering and moving the encryption, like an encryption hopping between entanglements. So like you bring one in, it's almost like ring toss, and then you take the message and you grab a green ring in, and then you have a blue ring, and then you throw it out. And so you're sort of like doing gonzo quantum entanglement bonding to keep in front of the quantum code cracking system by creating quantum bonding and moving. You're not making a face like you know what I'm talking about, because I certainly don't.
I'm still listening for the question.
Well, no, it's still like, are we also pushing forward with the quantum thing, like trying to assume that they will figure this out? How do you continue to encrypt things beyond that with like the next level, like whatever comes after quantum, like quintum or whatever it's going to be? Is there something going on in that realm too, where someone's not out in left field, but they're not even in the parking lot, they're across the street from where left field used to be, and they're working on the next level thing?
Well, the next level thing is related to this question of, is quantum mechanics the correct fundamental theory of the world at the scale in which these systems are acting, and where these technologies would be working? The question, is whether or not there are more fundamental physical theories that are actually describing entanglement.
Right.
So if quantum theory is the best complete description of the world at that scale, full stop, then these encryption technologies should work as advertised. They should be perfectly secure. And you're relying on the laws of physics to ensure that, rather than relying on somebody not being able to break a hard math problem, to crack that problem to break the encryption. When you're talking about the sort of assumptions about the world, whether you have realism, locality, and freedom of choice of your experiments, if any of those assumptions are wrong in any way, if you relax them a little bit, that opens up a loophole whereby a hacker, an advanced future sci-fi hacker, could potentially break these quantum encryption schemes. Let's say there's a more fundamental theory, and that, I mentioned before how we don't know how to unify quantum mechanics and Einstein's theory of gravity, general relativity together. Maybe in this theory of quantum gravity, there are pieces of information, degrees of freedom that this future sci-fi hacker could learn that would allow them to hack this encryption scheme that would appear to be unhackable if quantum mechanics was the full story. So the experiments that we're doing are related to asking this question: are these alternative theories still viable? We don't know in detail what they are yet, but these experiments can tell us some information about what they would allow. So in our cosmic bell experiment, we used light from these distant galaxies to set the measurements on the entangled particles, and we saw something that was consistent with quantum mechanics, consistent with what with the upper limit from Bell's inequality being violated. So we saw more correlation than would be allowed, and so, but because the universe is very large and very vast, the way that we were thinking about this is that we cannot completely rule out these alternatives from explaining the entanglement experiments. But if our assumptions are true, if Einstein's theory of relativity is true, then if nothing can travel faster than the speed of light, then these alternative models would have to have been in place acting billions of years ago in order to have something that's different from quantum mechanics explaining things. So when we use more and more distant galaxies, we're pushing the alternatives further and further back into a corner. And they have not been definitively ruled out, but we're narrowing the possibility space. And so what people want to do is they want to do an experiment where we try to close all of the known loopholes at the same time. I talked a little bit before about how we're trying to make these measurements very rapidly while the entangled particles are still in flight. And the reason for that is that if you make the measurements really slowly, if any information, like a phone call, had time to leak over from Alice to Bob that told Bob about Alice's measurement setting or her outcome, Bob could then immediately switch his measurement setting in such a way where he could use that to fake quantum mechanics even if quantum mechanics wasn't true. He could use that to artificially bump up the correlation between the measurement outcomes even if quantum mechanics wasn't at play. So that's a loophole which can be used to fake quantum mechanics. So you get around that, you close that loophole by making your measurement choices at the last instant while the entangled particles are still in flight. So there's just no way of any information having the time to go from Alice's side to Bob's side. Similarly, there's a loophole corresponding to, do I actually have freedom to make these measurement choices? Are they really perfectly free? And that, but by outsourcing the measurement choices to the universe, we're putting tension on that, and we're basically saying that if the loophole was going to be exploited, it would have to have been exploited a long time ago in a galaxy far, far away.
That makes sense.
And that makes it's more and more implausible the further back into space and time that you push the regime where these alternatives could have acted. You know?
I can't help but having this thought like looming right now on how cliche it may be, where people, the general population may say, or a vast majority of them say, well, all things happen for a reason. So there's this like predestined thinking. So no matter what, it's already happened. I think the only way to get in front of it would be to hack into or exist mentally on a time scale that's ahead of what we are doing right now, and being able to live or predict. And then all of a sudden, you can have a vast number of people winning the lottery because of that ability to predict or to perceive what's about to happen.
I mean, really, you're talking about some kind of time control, travel or whatever. To be
right, but it's almost like not taking it out of the mechanical and physics space and applying it to thought. Right? How fast can thought travel? Does that below the theory of nothing can, Einstein's theory of nothing can travel faster than light?
Yeah, so there's a lot to unpack there. So the question about whether or not things are predestined to happen or not, it's a very, very ancient question. And so when I was talking about classical physics before, that's an example of a deterministic theory. So, that means that things in the future are determined uniquely by things in the past. And that there's a way using physics to predict from the current state or a past state what any future state will be. And the power of how precise that prediction can be is limited only by how well you can measure the current conditions. There's always uncertainty in your measurements. So in practice, what that means for classical theories is that the time horizon where you can make accurate predictions is limited. And that if you make more and more accurate measurements where you have more decimal places of precision of the current state of some system, then you can predict how that system will evolve farther and farther into the future. So if the world is deterministic that way, then we actually do have the power to predict the future in a limited sense. In practice, there's so much uncertainty with measuring things like the current state that, like you take the example of weather prediction. There's so many variables that are going on, and that our computer models are getting better and better. Our computational technology is getting better and better. And I think that you'll notice that, over a decade, you now actually trust the weather report out to 3 days.
Yeah.
Whereas, like maybe when you're growing up, maybe you trusted it out to 2 days.
But I still don't know, like when they say that there's a 40% chance of rain, I mean, does that mean like 40% of the area will be covered by rain, or rain may or may not fall at all? 40%, like, I still don't even know that. Like,
well, it's a good question, and it depends on the definition. I'm not an expert in meteorology, but if you ask the question of, what's the probability that a raindrop is going to fall at this particular spot anytime today, then, if you have a fine enough computational grid, you can answer that question with a weather prediction model. But those are essentially classical model. Classical physics still works really well. You can use it to send rockets to the moon.
Yeah.
You don't need quantum mechanics to predict the orbits of planets or the orbits of rockets in the solar system. The fundamental question about are our choices predestined and, are things fundamentally predictable? If the world is governed by quantum mechanics, and if the standard mathematical formalism of quantum mechanics is correct, then the world is not deterministic. Then there's a fundamental indeterminism. This comes from this question of the quantum mechanical description of a system, which is often called the wave function, describes the system as having some probability of being here, some probability of being here, and it's not until a measurement is actually made that the system collapses into one possible outcome. And in quantum mechanics, this is an irreducible process. You can't do any better than that. Then you can't make a precise prediction. And that in quantum mechanics, there's also something which is related but different called the uncertainty principle, which says that there's certain types of quantities, like the position of a particle and how fast it's moving, that the more you know about one, the less you know about the other, and that you cannot measure both to infinite precision at the same time. So something like that already tells you that, if you had some idea that like, oh, how hard can it be to measure the positions and velocities of every particle in my body, that there's actually no way of physically doing that. So quantum mechanics introduces fuzziness and uncertainty at a fundamental level. The question that I and many are interested in is whether or not is it possible for there still to be something more fundamental than quantum mechanics that really does have a deterministic description.